All right, how many people know about containers? This is the Docker track, but you always got to check. How many people are comfortable with containers? Great, because I'm not going to dive deep into what a container is, but I will talk about containers in general. I typically don't like talking about containers because I think they're really like 1 to 5% of the overall problem. But this talk is pretty interesting, I think, because we talk about the need for things like standards, right? So we will talk about Rocket and AppC, which is the container spec from CoreOS in an attempt to provide an industry standard guidelines on what an application container is. And the first question we get is why, right? So early on, maybe even pre-Docker, a lot of people had this vision that they could use containers to build the perfect infrastructure, right? So most people, their first experience with a container, you go 5 minutes in, and things are fantastic, right? You have this in your mind. Whatever your infrastructure looks like right now, your initial belief was you adopt containers, and it's going to be beautiful. And then you go to production, and you find out that there's a lot of pieces missing, right? So you're deploying, but you don't really have like things like service discovery figured out. And then you discover things like the Docker bridge for the first time. And you find out that it's not really easy to get your host to communicate between each other. And in some cases, in some rare cases, you actually download a container that actually does care about what kernel version it's running. And now you have no way to address it because there's really no standards around this stuff. It's just new, right? So you move down that road, and what do? If you're a developer, you call your ops team, right? And your ops team sees you kind of wavering and things are looking bad. So you bring in your ops team, but again, there is no standards. So unfortunately, your ops team can't do very much for you, right? So unfortunately, this is how it's going to end. You actually have no choice in this matter. The good news is that things are improving. And one of the goals of this talk is mainly to provide an overview of application container spec, and we call it AppC for short. And then Rocket, which is RKT, is pronounced Rocket. And then I'm going to highlight where AppC and the Docker image format agree. So there's a lot of things people involved in AppC agree that Docker has done right, which is provide this idea that we can take an application and describe it as a single application that we can reason about. That means we stop talking about Java, that means we start talking about Ruby, and we just talk about applications, right? And the other part is there should be a config inside of that image that tells an executor what to do with that image, right? So what we want to do is write that down. What does that mean? And then we're going to, and I think to really drive the spec home, we're actually going to do something with it. So live, I'm going to take a set of Docker images, and we're going to convert them to ACIs, and we're going to see what that process looks like, just so we can see where things are the same and where things differ. And then we're going to talk about how to actually sign and distribute those. So one of the goals with AppC was we needed a stronger trust model. So if you're pulling random things from the internet, first, you should not do that. Don't pull random things from the internet. But one thing you would like to do is be able to pull something and validate where it came from, right? So if you've been managing systems for any amount of time, you've been used to this for your whole career, right? If you're using a package manager, normally those packages are signed from a specific entity that you trust. So when you bring them in, you kind of know who you're trusting here. We move to the wild, wild west these days where there's just things on the internet, and we're just like randomly pull them into our infrastructure. And this is especially dangerous when you start thinking about bringing in things like databases and key services that power your infrastructure. This is getting really, really, really dangerous for a lot of people. And then we're going to talk about how to actually do something with Rocket. Like, why did we build this, and how is it fundamentally different than other container runtimes? So first, at a high level, the application container spec. And the goals with this is to have something that is well specified, meaning we've documented every single detail on what an image is, how it should be executed, what system calls should be in play. And we wanted to build a community around it. So the goals were, the spec is no good if there's only one implementation of it. So we're trying to foster other people to implement. And there are actually a couple of implementations of the application container spec. So the number one thing is the image format, right? The image format is called an ACI. Second is a discovery mechanism. So when you build one of these images, you should be able to host it wherever you want. So that means if you have a web server and you want to just throw your images in there and just serve them to your organization, you should be able to do that. There's no special registries. There's no default registry. So that's good and bad in some ways. The bad part is there's no central place to go to find all the ACIs in the world. The good part is you don't need much tooling to host any of this stuff. Everything in app container specification was meant to be simple. You can build an application container spec or image with command line tools, right? You can use tar, gzip, and GPG to sign them, and you can just build your own image. No fancy tooling required. And then the runtime environment. So once you do have an image and you can find the image, the next thing you need to do is be able to specify how you run the image. So if you want to be compatible with application container spec, you need to do a certain set of things so that people can kind of rely on behavior even across systems. And then a set of tooling to help build, validate, and help people just in general get application implementations correct. And the first thing I'm going to talk about is the image format. So the image format is very similar to the Docker image format here. Pretty much the starting point for application container spec. The ACI needs to contain everything that the application needs to run. And if it doesn't, it should at least specify the mount points that need to be added to make it so. So if you think about it, if you're using Docker and you have an image, the image tells you a few things, maybe its entry point, but it doesn't have to tell you all the volumes it requires. You're free to just bind mount in anything and then map wherever they want, right? So there's some advantage there. There's flexibility. But you can't read the image manifest inside of a Docker format to know the required mount points for an image. So if someone writes really good documentation, it'll be really easy to pull it down and mount things in. But it'd be much better if you actually ran the image and it said, you didn't mount in all the required mount points. This won't run. We can do that in AppC because we make it a requirement. So there's two main things. There's a root file system, same thing as Docker's image format. And the root file system is just that. Some people will take an existing system and you can tar the whole thing up and make that your root file system. You can use Docker build to produce a root file system. It's probably the most popular way of producing root file systems these days. Or you can use native system tools. Debian and Red Hat have good tools for building full systems in a true root. And then you need an image manifest. So for a very simple ACI, this is one from a project called Kubernetes for managing containers. This is the API server. And it's a statically linked Go binary. Actually, this one isn't statically linked. I'm going to bind mount in some libraries from the host. Normally, you wouldn't do that. Sometimes you would just say, I'm going to build on top of Debian. But I'm a big fan of containers that are about 10 megs. I do not like downloading containers that are like 500 megs or a gig. And there's ways you can get around that on the manifest. So if you visit the spec, it has details on each key that you can find or describe in the manifest. Now, these manifests are versions, so this is the 0.5.1 version of this manifest. And an executor can read that version and know what it can find inside that manifest. Now, this is incomplete, so I can fit it on the screen. But this tells me the name of the application container. The version is basically similar to a Docker tag, and it's up to the executor to reason about what that tag means. It could be a semantic version. It could be anything. And we do have the concept of an OS, right? So one of the goals with application container spec was to work for multiple operating systems. In order to do that, the images need to have some sort of metadata to tell you this will work for FreeBSD and this will work for Linux, right? Containers have a shared kernel. They just won't run anywhere. So what we do is we provide some metadata to help the executor understand if it can actually run that container or not. And then we have an entry point called exec. So this is basically similar to the entry point you would find in Docker, user and group. And then the mount points are specific. So here I'm specifying that I need the SSL search from the host. So my static link binary will try to search this local file system for certs, but it won't find them. So what I'm specifying in my image manifest is that those need to be passed in at runtime. If they're not defined here and someone mounts things in, won't work. You have to be very specific about your intention in application container spec. Then a discovery mechanism. So one of the goals was we wanted it to be easy for anyone to build and host their own registry. The Docker registry is actually really, really, really powerful, but it's actually complex. So complex that you have to go find one in order to get started. And there's some good open source ones out there, but sometimes you want something super, super simple. And in this case, we're looking at a ACI, and all ACIs by default must have a detached signature. When you attempt to install one, container runtimes must check to see if there is a detached signature and do the verification process. Now, you can turn it off, but we do make you jump through a flag that says insecure, skip verification, so that you know you're doing something that you probably shouldn't be doing. So in this case, we have these 3 artifacts and the public keys, so that way an executor can download those public keys and use those public keys to verify the image. Now, there's simple discovery. And in simple discovery, you take your artifacts and you put it behind any HTTP endpoint, doesn't matter. Throw it on Nginx, put it on S3, Google Storage, it doesn't matter. You refer to the full URL. And then what will happen is an executor will follow a convention. It will take your URL and fill in the blank. So that's a template that we see there. So it'll take the name of the ACI, the version or that tag, and the extension will be ACI. And then by convention, it will look for ASC, knowing that that's the actual detached signature, and attempt to do the verification. The other option is meta discovery. So let's say that you have an executor that may have different capabilities. Maybe you want to distribute your images via BitTorrent or some other protocol. So what you can do is you can give the executor hints. And you can also have a different place where you store your actual images. So maybe it's not on the same server that's serving up the metadata on where to find the image. So in this case, we can hit an endpoint, and all you have to do is return back this HTML header, right? And the header is only a template to tell the executor how to fill in the blanks to find what it wants. All right, so I hit this endpoint, and I get the AC discovery tag back, and it tells me that the content you're looking for, so if you match this name, use this template to actually download what you're looking for. If the content isn't there, then you'll just handle it through the normal HTTP process it's not found. And then down here, we get the public key, so I have the ability to pull those down during the discovery process. And this was designed because we feel that people will probably want to do something outside of HTTP, S3, maybe even something like BitTorrent if you have lots of hosts. So you want to know where we can find the entry point for that stuff. Then the runtime environment. So the other half of this story is you have an image, now you got to run it. So AppC defines how ACIs are executed on a particular host. So one thing we need to talk about is like our file system layout. So in AppC, we have this concept of a pod, and we'll talk about that a little bit more later. But we got this idea from the Kubernetes project of the ability to compose a collection of containers into a single execution unit. Now, this allows some really interesting patterns. You can take 2 distinct apps that need to run together and have them be independent ACIs, and then compose them into a pod construct and be guaranteed that they'll share the same execution environment, meaning that they have shared namespace, so they can contact each other or localhost. They optionally can share mount points between each other, and they can share their isolators, meaning how much CPU and memory the combined unit can have. Now, once you have a pod concept, it makes it really easy to schedule across a cluster. You can say these things must go together. And you don't end up in a situation where half of your dependencies land on a host, and the other half may be pending and can't find a home and get scheduled. So you resolve that by having a pod. Volumes, like we saw earlier in the manifest, how volumes are actually managed or how they're mounted. Executor's job is to do that. By default, you need to be able to handle various networking. So we have a networking implementation or standard. Won't go into details there. But one of the implementations of AppC, which is Rocket, has support for network plugins. So you can do things like IPVLAN or DHCP, something similar to the Docker bridge, your choice, you bring in your own plugin. And then resource isolators. On Linux, that would be C groups, right? The ability to specify CPU limitations, memory limitations, disk I/O, network I/O, all the things that the kernel supports, you can express those in a form of isolators. Now, isolators will be different for different operating systems because they mean different things. But in the case of Linux, you're basically just describing C groups. And then logging. It also specifies that the runtime is responsible for handling logs for all of the pods and the containers running in them. Then there's a set of tooling. So the default tool that ships inside the application spec repository is called AC tool. And what AC tool will allow you to do is build a container. So let's say you have a CI system and you're building your application. What you can do is line up the root file system for your app, put everything in place with just regular move and CP commands, and you end up with this directory structure. And what you do is you add in a metadata file describing how that particular application should be executed, and you run AC tool build, and it spits out an ACI. Or you can do this with just command line tools. You can just basically do a tar and gzip on that, and that's the same effect. The next thing you can do with the tool is also some ad hoc things. So let's say you pull down an ACI and you want to look at its manifest. You can print it out from the command line to see what the user's intention was. You can also validate these manifests. So again, standard tools to pull the manifest out using tar just to fetch a single file. Once I have that single file, I can validate that manifest, or you can validate your manifest before you build your ACI. You can also validate the actual ACI as you build it. And there's other tools for validating discovery endpoints to make sure you've done it right. And finally, the AC tool can also be used to validate an implementation of the spec itself. Right? There's a couple of ACIs we can use to give to an implementation to exercise to see does it actually implement the spec correctly. Another piece of tooling, the last one I'll talk about, is Docker to ACI. Right? So Docker's ecosystem is vast. Right? That's where the majority of the containers live. And there's, between Docker's image format and appc, they're so similar that we can pull one down on the fly and convert it. So you have multiple options. So if you're running, let's say, Rocket, Rocket will take a Docker endpoint, grab that container, convert it on the fly, and just execute it. Sometimes you may want to switch things up a little bit. So in my case, and we'll see in the demo, we can use Docker to ACI to download the Docker container from, in this case, from the Quay.io registry. I'm pulling down this container, and you notice that my container is pretty tiny. It's like 7.8 megs, just a binary in its compressed form. And then it starts converting it to an ACI. So it downloads all the layers. And the nice thing about this tool, it works on any OS where you can run this Go binary. So from my Mac, I can actually download all the Docker layers. And what will happen is it will start converting things. So in your Docker file, if you use the volumes directive, Docker to ACI can pick up on that and actually create all the metadata pieces we need to represent the volumes that you would need in your ACI automatically for you. And then it just pops out the result. And we'll actually go through this. So the other part of ACI, or application container spec, was we wanted to have multiple implementations. In order to have a really validated spec, you need more than one implementation of it. So there's a couple of libraries, appc being the one that we use inside of Rocket. And there's some C++ libraries. And there's also some runtime implementation. So very shortly after we published the spec, someone came through with the FreeBSD, Jails, and ZFS implementation of appc. That was really awesome, and they did this independently by just following the docs on the site. Kruma, which is a container management and orchestration tool from a company in the US called Upstart. And that's pretty interesting. They have this container OS that basically runs application containers, but was designed to be like this cohesive whole. So it's just a clustered OS by default. And they just chose to use appc because it was specified enough for them to avoid implementing their own thing and follow standards that were already published. And of course, Rocket. One thing about Rocket and its runtime implementation, a lot of people don't know, at a very high level, there's some details there, but at a high level, what Rocket does is it takes these root file systems, and we have these things called different stages, stage 0, stage 1, and stage 2. With stage 0, our job is to download all of those ACIs and construct a file system. So you can imagine doing this where there's a Java ACI that just has your JVM. There's another ACI that actually has like your WAR file, your application. and maybe some other things that need to run on top. And what we can do is we can construct this and lay it out into a final root file system. And what we do in Rocket is we take that root file system and we give it to systemd inspawn and let it manage the process for you. And the way we make it work with systemd inspawn or systemd in general is we look at your manifest and we can automatically generate systemd unit files for you and say that here's the execution point, here's the commands you need, here's all the bind mounts you need, and we can turn it over to the OS to manage your application for you. So then you inherit all the benefits of something like systemd, and we'll see what that looks like. All right, so before we get to the demo, we're going to talk about Rocket a little bit. And then we're going to get hands-on with this so you guys can feel the actual flow for this. So Rocket, we had to change our name because of name clashes with other projects. So we just call it RKT, but we still pronounce it Rocket. So Rocket is a CLI tool for running app containers on Linux. That's specific, right? There's no plans to make it work on any other platforms but Linux. We hope to see other implementations on other platforms using their native constructs. But Rocket won't be that universal tool to do that, at least today. The important thing to understand that Rocket has no daemon at all. Right? So there is no Rocket daemon that runs that you interact with. You know, Rocket runs in the foreground. And this works well with systems like Upstart and systemd because they will take over and manage the process going forward. So we have to do some really tricky things. If you have a command line tool that has on-system store where you're storing all your images once you download them, then you have to do things like file system locks and advisory locks to make sure that multiple instances of the CLI don't start colliding and overwriting data. But we handle that the old-fashioned way with basic file locks. Now, one thing that's unique in Rocket is that the execution engine is swappable. So what I explained earlier was that we use systemd and systemd inspawn to take your ACI and run it. Ideally, you could use libcontainer right from the Docker project and do the exact same thing. You just have to interpret the metadata and do what you need to. Or in the case of Intel, they actually take your ACIs and run them in a very specialized VM that runs in KVM that gives you not too bad execution speed. They come up in about 150 milliseconds. And the nice thing about it is, you know, people that are worried about container security, you probably should be worried about container security because it's not meant as a security boundary. It's meant more to kind of give you isolation. If you throw it in a VM, you kind of inherit that walled garden some people are looking for. So what Intel does is they take Rocket and add a different execution, stage 1, where they just throw it inside of KVM and boot it from there, right? But the workflow feels exactly the same. You have an ACI, you give it to executor, and the executor just chooses this backend that it wants to run under. Or you have the option of just running Docker images straight from whatever registry you have. Works just fine in most cases. And it's friendly with init systems and cluster orchestration tools. So one thing we wanted to do was make sure Rocket was small enough to be something you build platforms on top of. The good news is a lot of the work we've done in Rocket and the collaboration that we're doing with the Docker team is to try to get some of the same modularity inside of Docker. So it would be nice if you can take Docker and run it without the daemon. Or maybe take Docker and run it with only the build steps, right? Or have Docker do something where it just runs in the foreground and allows something like systemd to take over. And then pods are that unique concept again. You can run one or more containers in a single execution unit. And if you do that, those pods get shared namespaces and optionally volumes. So we talked about systemd, and here's a little bit more detail. Intel calls their implementation clear containers, right? Intel has done a lot of work and investment in getting VMs to be fast with their VXT extensions and all the security that they've done around it. So what they decided to do was to take a lot of the other technology that you find in the kernel, and they actually figured out a way to speed things up. So most VMs today boot in, I don't know, seconds, sometimes minutes, depending on your platform. But seconds are really slow in comparison to what you get from a container runtime like Docker or Rocket. So what they've managed to do was figure out how to build a very thin OS, just enough to get you to Docker, right? Even skipping the BIOS boot process because they don't need it, right? They know that you're not going to be trying to run a full system there, so you just skip the whole thing, and you go straight into the kernel, into Docker, and you run the container. Doing that allows them to get the overhead way down. So you're going to have an additional 18 to 20 megs of overhead on memory, but you get all the things that we used to before. So if you have some KVM management tools, guess what? They just work. If you have that fancy overlay networking thing that you're using with KVM, it works. You want to use OpenStack management tools with Rocket, it will just work. And the same thing can possibly be applied to Docker by building another execution backend. All right, so here's how Rocket works at a very high level. So remember I said by default, you have to trust the images that you're pulling down. Now there is a flag where you can skip the verification, but we try not to promote that idea. We want this idea where, in this case, if I want to download this Kubernetes set of binaries or ACIs, I need to trust the public key first, right? Key distribution is a problem. Trusting keys from people is a problem. But once you do trust someone, this is how you add it to your store. So in this case, I'm making this a root key saying, you know what, anything signed by that key, I'm willing to trust. Now you can scope this down and say, you know what, I trust that key for a single ACI image. That's it. Or maybe from anything from a specific domain. If you want to just download an ACI and verify it, you run the Rocket Fetch command. And once you've downloaded a few of these things, you can call the images to see everything that's installed on your system. Now, one thing to keep in mind, when Rocket downloads an ACI, we store it by its hash, right? So a lot of people are thrown off when you take a container and you call it, I don't know, 019, and you push that tag up. Well, anyone's free to just overwrite that tag again, right? And guess what? 019 is this new thing. It was something else yesterday, but it's this new thing today. And that will throw you off because it doesn't behave the same way, even though it has the same name. So in Rocket, when you go and fetch a container, we take that, we make a hash of it, SHA-512, and then we store it in a content addressable store, meaning that when you want to run that thing again, we look up the index and we run that hash. That's it. We're not going to go fetch something because it has the same name. If you don't match that hash, we're not running it. If anything is thrown off with the contents on disk, it's going to be broken. Right? This gives people a little bit more security and reliance on what you actually have. The great news is, in Docker's V2 spec, they're planning to do the exact same thing. So if you've seen some of the work in Docker V2, you can actually address containers by their hashes now. Right? So this is very key to actually having kind of this immutable infrastructure or something that you can actually trust. So that's excellent to see. Now, when you want to run a pod, when you launch a pod, even though you're, in this case, I'm running a single container, they still run in a pod. Here's what you do. Now, this is kind of verbose. Rocket does have config files. So if you didn't want to specify this on command line, you can actually put it in what we call a pod manifest. So it's basically like a JSON description of all the flags that you need to pass, all the volumes. And then you can just pass config files to Rocket instead of all these flags. But here I'm showing it this way for simplicity. So inside of our ACI, we specify that we need some volumes. And then at runtime, we map those volumes in. And we have to be specific. The volume comes from the host. We can also mark them read-only, very similar to the way Docker handles volumes. And then here again, we're specifying the ACI that we want. Now remember, once we use this name and we do download an ACI, future runs will use the hash instead of going back out to the internet. And then the rest of these are the flag passed at the entry point into the container. Very similar to what you do in Docker. And then if I want to list the things that are running, we run the list command. And you also have the ability to use the other systemd commands like machinectl, because when we run a Rocket container, we register with systemd, and all the other OS tooling just works. Journal, everything else in the OS is fully integrated. And then finally, when you run a lot of containers, I don't know how many of you run into this. You're running containers, they die, they come and go, they come and go. And then you do like docker ps-a, and you're like, whoa, who did that, right? And then you're not really sure on which ones you can delete, because you might try to delete one that's actually still being used by someone. It's hilarious when you do that. So what we do in Rocket, we basically took a very simple approach to garbage collecting the containers. We're like, okay, if the container isn't running anymore, and it's being referenced by no one else, then we just do this one part where we sweep. We just say, hey, we mark all the pods, we move them into a different directory on the file system. Implementation detail, but we just mark them. And it gives you time to, like, hey, maybe start it again. And then we have some policies. So by default, every 30 minutes, we go through everything that has been garbage collected or marked. We sweep them. They go away. And we did it in a way where you can actually run that command inside of a cron job, right? So you would mark them on your timetable, and you sweep them on your timetable. Or you can just do them manually. Again, there's no daemon, so you're free to figure out how you want to do this. And then this is how you run Rocket with systemd. Upstart will look something similar. So this is a normal systemd unit. So instead of running a binary here, we run the Rocket command that we saw on the command line earlier. And then you get to use the rest of the systemd process management, meaning restart policies, all the other error checking. And another big one to me that I think is really powerful and most people overlook is the ability to depend on another service. Right? Like, do not start this service unless this other service starts. Right? So systemd kind of gives you that for free. We're not going to try to implement that in Rocket. Let a better process manager handle it. And then you just use your normal system tools, right? So on the first boot, this thing will be downloaded, stored in the content addressable store, validated. If everything checks out, it will run. If not, it will fail, and systemd will tell you, hey, here's the error we got from Rocket, invalid container, it won't run. All right, so that's the overview of appc and Rocket. So what I'm going to try to do now is run through the conversion of some Docker containers. We'll look at the Docker files and just see what it takes to make them ACIs, right? And I'm going to try to pick a complex set of things. There's a project called Kubernetes by Google that allows you to manage containers and scale. So what I've done is, and I like to use Docker a lot actually, so I've made Docker containers for each of these things, all right? So I did it in a way where I actually used something like Compose to spin up a full Kubernetes cluster. If you're interested in that, you can check out those details. But what we're going to focus on here is basically I created a bunch of Docker containers that look like this, right? Very simple. I do my build in CI because I don't like big build containers. So I take my artifacts, I copy them into place. And what I'm doing here is specifying every single volume that I plan to map in the future. I'm doing this to give hints to the ACI tools for conversion, right? Because without this, I will have to do some weird things, and I'll show you some of those issues. The most complicated Docker file that I have in this whole stack is the kubelet. The kubelet is interesting because it interacts with the host, and it needs to do some weird things to the host, and it has a little bit of trouble running from a container. I need to know the host's release. I need to actually be able to inspect things that Docker's doing. I also need to run some binaries that live on the host, and I need to do some hackery. I need to use nsenter to enter the namespace of the host so I can do mount points there, so that way when things are mounted via Docker back in other containers, it still works. So this is pretty complex image that when I run it, I'm going to have to mount a few things in. So I specify all the mounts. Now, you guys know what building Docker images look like. So once I have all my images built, and this is the part where we'll do a bit of a walkthrough. So what I want to do is take all my ACIs that are running in Quay.io and convert them to ACIs. All right, so the way we do that is we'll use the Docker to ACI tool. So I've downloaded them in case Wi-Fi doesn't work, but we'll try a couple of them so you can see the idea here. So we'll start with, let's do the API server. So what we do here is we run the Docker to ACI command, and we give it this prefix, Docker : colon slash slash, that knows it needs to go out to Docker. And what will happen here, Wi-Fi, please work, is we'll start downloading each of the layers, and once we have them all on disk, we'll go through the conversion process, meaning we just want the root file system. And if you ever looked inside of a Docker image, there's a bunch of other root file systems that make up the different layers. We take all of those and just combine it and basically flatten the whole thing out. We rip out the metadata from Docker, look at it, it's a JSON file, and we convert it and map the keys that make sense. And then we end up with something like this, right? So once you have one of those, you can use AC tool to cat the manifest. Let's see. So there's a couple of commands here. We can cat the manifest. We can do some validation to make sure the thing that actually converted actually works. If we want to, we can cat the manifest file. come on, manifest. And then we're going to print it so we can actually see what it looks like without a mess of JSON on my screen. And we downloaded the kubelet, so that's Kelsey Hightower and kube API server. And that's what the conversion looks like, right? So the tag we got from Docker ended up being our version. The name is Quay.io. I actually don't like that name, so I want to change this, right? But I don't want to manually go in and rip this thing down and put it back together. So what we can do is use the patch command. So I can actually patch some ACIs. So here, and I'll just put this on the terminal so you can see it a little better. We can call the ACI patch manifest command. I can rename the ACI. And that's all I really want to do for this one. And what's happening here is the ACI is being ripped apart. The manifest is being grabbed out, updating some values that we want, and it's being put back together. Now, those are all pretty simple. But the one that's a little bit more complex is the actual kubelet. One mount point that I can't do in ACI, or that Docker won't allow you to do, is mounting in etcresolve.conf. Right? That's added at runtime by Docker. If you try to specify that as a volume, Docker won't allow you to build a container. So what I have to do is do it after the fact. So I'm going to patch that in using the patch command. So for the kubelet, we'll run this command, and we also need to run it as a privileged container. Now, in Docker's manifest, there's no way to say that this needs to be a privileged container. But in ACI, I have to specify this. So in order to do that, I can specify mounts that I need to get resolve.conf, and I can actually specify a few more capabilities here. So once I have that, I build my new container. And if you notice, I'm actually renaming all of these containers as I go through this, right? So I'm stripping off my prefix from the registry. So I'm going to go through really quickly and convert the rest of these. And once I have these done, the next thing we have to do, we have to sign them, right? So signing is pretty straightforward. You do everything with GPG. So if you have experience with GPG, what we can do is we're going to export the public key for my signing key. And this is so I can host it on my endpoint. So that's the public key that we can trust later. And then we can go through and start signing our ACI. So I'm just going to use this for loop. And we're just going to go through, for each ACI, we're going to output a detached signature for each of those things, right? So we're going to sign them all. Now this may blow up because I haven't converted all of my ACIs over. Let's see what happens. All right, good. It signed the ones that were in place. So now I have detached signatures for all of the ACIs, right? So those are all the artifacts I need. Now once you have those artifacts, I'm just going to store them in a file bucket on Google Compute, right? So this is how you distribute them. So you build them, you sign them, and you host them to where you want. Now Rocket does support, I think, things like basic auth. So if you want to put them behind some authentication, you can do that. And that backend is pluggable, so you can add other authentication mechanisms. So here I'm hosting everything that I need. The next thing we need to do before we can launch these containers is we need to trust the key. So what we do is we hop on our machine. So here's the machine running Rocket. And we tell it to trust that particular public key. And we're going to make it a root key. So it's asking me, are you sure you want to trust this particular key? So this is my Rocket Science signing key. And what happens is it gets stored into the key chain that lives on the server. Again, everything can be done with simple command line tools. So if you want to know all the keys that live on your system, you can ls rocket trusted keys directory, and they're all stored in there by their fingerprint name, right? So anything that has that fingerprint, that key will be used during the validation process. Now, once you trust these things, you can run Rocket on the command line, but remember, it'll be pinned to the foreground. So what you really want to do is create systemd units for all these things. And I've, ahead of time, put the systemd units in place. So here I have a systemd unit for all of these services. If you look at it, and some of them have dependencies on others. Most of the services here require that this API server be up and running. And here I'm doing the full configuration for Kubernetes. And what I want to do, if you look at the controller manager, it also requires the API server. But we're just going to let systemd work that out for us. And we're also going to let systemd handle the restarts if this were to fail, all right? And also running in the foreground, which Rocket does by default, that means the journal is fully integrated. So all logs flow through the systemd journal, rotations handled, and all of those things. We don't have to go look for logs for our actual containers once they start running. So at this point, we can just start these things. So let's see where we are. OK. So we can enable them if you want them to start automatically at boot time. Or you just call the start command for systemd. So we'll do this here. We'll do the controller manager. It really doesn't matter what order I start these in, mainly because the actual binaries themselves are smart enough to wait for their dependencies to come up. We'll start the scheduler. And then we'll finally start the kubelet itself, all right? Now, you can, from here on out, you can actually use systemd commands to figure out things about your processes, manage them that way if you want, or you can use some Rocket commands. So I can do Rocket list, and I see that all of my containers are actually running. We also have integration with machinectl, so we can list them, and the machinectl, Rocket does is it registers all of your containers with systemd, and then you can start using the machinectl tools, and they're all addressed by this hash. And once it's up and running, if everything is working correctly, we should be able to see Kubernetes actually working, and it does. We can actually see that one of the nodes got registered in the system. So what we've done here is we've taken a set of Docker containers, we've converted them to ACIs, we've signed them, we patched them, we put them into an upstream repository, we created some systemd unit files for them, and then we referenced those ACIs that we built earlier. And now we throw them in systemd units, and we let the system take over and manage our services, just like we were doing before for like RPMs or static Linux distro. And now we have a full Kubernetes single node cluster up and running. So with that, I'd like to conclude the presentation and open it up for questions. Thank you. I'll take that first question.
Is it the person that creates the image that signs it? Or is it the repository that signs the image, if you see what I mean?
So the question was, who's responsible for signing the image? You always want the responsibility to be the person that's distributing and building the image, right? That's the trust relationship you want to have. So not with the repository, because who is the repository, right? A single entity signing all of the images. Number one, if they didn't build the image or it didn't originate for them, it's really hard for them to be responsible. So ideally, if you can get it closest to the person that's actually building or compiling or writing the software, that's the entity that you want to trust. Yeah, so trust is hard, right? Like if you want to, so the question was, follow-up question was, then you need a key for every follow-up image. So there may be a world where you do have someone that will curate content. There's nothing stopping someone from becoming the centralized distribution that has some type of qualification process to say, hey, we vetted these things and we trust them, and then you establish trust with those entities. Since they're detached signatures, they can be re-signed, right? So you can have many signatures for them, right? So since it's not baked into the actual image, you're free to go grab these things and re-sign them for your own entity and say, yeah, we trusted the person, we've downloaded it, we validated it. Now let's move it into our own repository and we'll re-sign them with our key, right? And then you trust that key instead. Good question.
I noticed that.
Yeah, so the question is, all the commands that I've been running so far, like this rocket list command, require sudo, right? And the question is, can you run Rocket as a non-root user on a system? So we're working on that. The main issue is that access to the cache where everything is stored. So if we look under var lib rocket, this is where all the content addressable stuff is. So all the blobs, all the hashes, and that's a secure location. And the only person right now that we allow to read that is root. So we got to figure out a way how we can divide these privileges up, right? So what we want to do is have the ability to download content as any user, view only, probably as authorized users, but then runtime will require the permission needed to run a binary on the particular system. So today, right. So this is what we're getting at. if we have to figure out what that model looks like. From a UX standpoint, it's easier to centralize it all, but you can imagine a world where there's like containers that get installed locally into your user directory and they only live there, right? So since it's file system based, there's really nothing stopping us from saying, here's one set of trusted keys, here's one set of CAS for all the images, and that's just local to your particular home directory. And then things launch and live there only, right? So we set ourselves up to be able to do that, right? It's just a matter of priority. Good question. Any other questions? Cool, well, fantastic. Thank you guys for attending.